Okay, so we're going to do question 1A and we're also going to do 1B. So it's conservation of energy problem, and let's get started. So a large chunk of ice with a mass of 15 kilograms falls from a roof 8 meters above the ground. So we have to first find the kinetic energy of the ice when it hits the ground, which is the final kinetic energy. And then once we've done that, we find the speed of the ice when it hits the ground. So that's like the final velocity, right? So first thing we're going to do, what we always do with all these problems, is we write down what we have off to the side, what they give us in the problem. So I see that they give us mass, which is 15 kilograms. I see that they give us height, which is 8 meters. And I also see that we indirectly have gravity, right? Because if we're talking about Earth, we know the gravity is 9.8 meters per second squared. Cool. So we have our mass, we have our height, and we have our gravity. Okay? So let's look at the formulas to make sure we're good. Hopefully you guys got your formula chart, but if you don't, let's put them up here. So we know kinetic energy is 1/2 times mass times velocity squared. And we know that potential energy is just mass times gravity times height. We happen to have everything for potential energy. We don't have everything for kinetic energy. We have our mass, but we don't have our final velocity, right? But the good thing is, when you're dealing with dropping things from certain distances, you know that the initial potential energy will be the same as the final kinetic energy. So let's write down our formula. So we know that our formula is straight up, not kind of broken down. Our kinetic energy initial, so our beginning kinetic energy, plus our beginning potential energy equals our final kinetic energy plus our final potential energy. So knowing this, without kind of breaking it down, we know that when you're holding an object up with a certain amount of height, let's say you're standing on a roof and you're holding a softball or whatever, when you're holding it, it has no initial kinetic energy because the velocity is 0, right? So if this is 0, everything else is 0. Also, when you drop that softball and it hits the ground and it's just sitting on the ground, it has 0 final potential energy because the height is 0 at that point, right? It still has a mass, still has a gravity, but the height is 0, everything's 0. So what we can do now is we can start zeroing out stuff in this equation. We know that the initial kinetic energy is 0. And we know that the final potential energy is 0. So that's good. That kind of eliminates stuff for us. Now what we're going to do is we're going to break this formula down. So we're going to go mass, because potential energy formula is mass times gravity times height equals 1/2 times mass times final velocity squared. Or we know that this is just the final potential energy. Okay? So let's plug in what we got. We have the height, or we have the mass. Let's start with that. So is 15 times gravity, 9.8, times height, which is 8, and that equals, I'm going to change this back to look like this, our final kinetic energy, right? These are all the same. So let's punch that in the calculator, see what we get. Hopefully you've done it this way. So your answer should be, let's flip this around, our kinetic energy final equals 1,176, and then we always have to have the unit, so our unit for energy is joules. Okay, so that is our final kinetic energy. So we've done that one. Now, which is what they asked for, find the kinetic energy that's when it reaches the ground, which means, that means they're talking about the final, right? Not the initial. Because if it was the initial, it would just be 0. Okay, so let's look at B. What is the speed of ice when it reaches the ground? So first off, let's just look at our formulas. I mean, let's look at the top. There's no speed in this one, no velocity, but there is in this one. So you already know you're using this formula, right? So what we're going to do is first, we already have our data here. Let's write the formula. Kinetic energy final equals 1/2 times mass times velocity squared. Okay? So we know the kinetic energy, right? So we don't actually have to solve that. So we know 1176 equals 1/2. We know the mass. I'm going to put it in parentheses. Our mass is 15 times our velocity squared, right? So the only variable we have is velocity squared. Okay, so let's combine what we have. So we can do 1/2 times 15, and we know that is 7.5. So I'm just going to do my arrow knowing that I combined it. 7.5 times the velocity squared equals 1176. Okay? Now we need to get that velocity squared by itself. We want it alone. Okay? So what we got to do is, since these are multiplying, we got to divide it out. 7.5, that cancels. We got to do the same thing to the other side. 7.5. So now you have 1176 divided by 7.5. Okay? So that should be, you should get about 156, we'll say 0.8. You can round it if you want. Equals velocity squared. Now, is it saying what is the velocity squared when it reaches the ground, or we just want to know the velocity, right? We just want to know the velocity by itself, so we got to get rid of that square. So what we need to do is we need to do more or less the opposite of square, but we'll just say what we need to do is we need to get rid of that square by square rooting it. Okay, so we're going to square root this side. And we know the square root of velocity squared, or a variable squared, is just velocity, which I'm going to flip it because I like my variables to be on the left. And now we got to square root this side. So now we got to do the square root of 156.8. And our answer, our final answer, should be about 12.5. You know our unit should be meters per second. And it's just velocity, so that's not squared. If it was acceleration, we would square it, but it's just velocity. We're going to box our answer, and that is it. That is question 1A and 1B. Most of these are very similar. You'll be using very similar formulas. So there you go.